Good. Thank you, everyone. It's been great being back with you. Oh, should I do it in English or in French? English, like
English.
We all like topology here. We all love topology. And so today I'm going to try to bring you into my world of topology. So this is a world where the notion of topological spaces is useless. And so it's a bit of a challenge because topology is not about topological spaces. What else? I'm going to try to introduce a couple of ideas to convince you that topological spaces are not the only way to do topology, to encode formally a space, and that there's a need of other notions of spaces. So let me start by recalling some facts. So we're gonna move down in the separation scale. So at the top of the scale, there's going to be the most separated spaces that we can think of, which are essentially discrete spaces. I'm going to call them disconnected spaces. Yes, not only I want discrete spaces, but I want something like spectra of Boolean algebras. Kind of thing. So it's basically a bunch of points put together, like the contour set is going to be there. After that, there's a good notion which are the completely housed-off spaces. So that's essentially R, manifolds, and the spectrum of C-star algebras. So it's basically the spaces that whose topology is completely determined by R. Then we have the housed-off spaces. Like any subspace of R. And below housed-off spaces, we start with the bizarre spaces. So that's the so-called T1 spaces and T0 spaces. Maybe you remember that. I'm going to give the definitions in a minute. So an example of T1 spaces is the cofinite topology on R on N or R. And T0 spaces. We have examples include the Alexandrov spaces. I'm going to recall what they are in a minute. And these are spectral frames and those very ugly spaces. And but compared to the kind of spaces that I'm going to be interested in, these are very nice. I want to work here. I want to work below those spaces. And example are going to include bad quotients, or foliations, or group actions. So yeah, typically leaf spaces. moduli spaces, and these are things like the space of sets. So hopefully by the end of the talk, you're going to have an idea of what is this space of sets. It's a space whose points are supposed to be all sets. What is best? Did I change board or not? I lift it and people can see. Yeah, then we can come back. Yeah, maybe it's best.
We go here, then we not see anything.
What?
If you go here, they will not see anyway because we...
Well, yeah, but you're going to come back with the Zoom more quickly. So that's the program. The program is to arrive here. So we're going to go slowly. And hopefully you're going to understand why I'm mentioning the one at the beginning in a moment. So some spaces are so badly separated, then the notion of a topological space cannot describe them anymore. So here, this is the limit of what topological spaces can do. Okay, so we need to understand why there's a problem with topological spaces. And how to solve it. So I need to start with some recollection. And the protagonist of topological spaces, the main protagonist is the Sierpinski space. It has two elements, 0 and 1, and the topology is the only non-trivial topology. So there's the empty set, which is open, the singleton 1, and the whole space. So the point 1 is open, and 0 as the complement of an open is closed. So this is not the discrete topology, and this is not the coarse topology. So what is this space, and why is it so important? If X is another topological spaces, what is a continuous map from X to the Sierpinski space? It's a partition of X in 2, which are the preimage of 0 and 1. And 1 being closed, the preimage of 0 is going to be closed. And the image of the preimage of 1 is going to be open. And so it's a partition into an open and a closed complement. And so because of that, there's a bijection between the open subsets of X and continuous function from X to S. So to an open, I associate the characteristic function, which value is 1 if X is within the open, and 0 else. And in the other direction, I get the image. So this object, so topology can be understood as studying functions with value in this very particular space. That's why this space is so important. I mean, sometimes we study a space with function with value in R, say, but in classical topology, if we're only interested in the open subsets, that's function with value in S. And so first one. So this is an algebraic device. An algebraic object. It's a sort of a ring. The precise structure is a complete distributive lattice, also called a frame. And it has arbitrary unions. As it happens, it has arbitrary intersections, but we are only going to look at finite intersections. And there's a distributivity of intersections over arbitrary unions. So this plays the role of a sum, this plays the role of a product, and we have some distributivity. So this is a kind of a ring. And so somehow we can understand general topology as the study of this kind of rings. And so we can prove that we can recover the whole of topology just with the structure of those rings. That's not my purpose today, but we're going to need to keep this in mind. So I want to keep this. So if I have a continuous map between two topological spaces, then I can pre-compose with my map, and I get a function between continuous map from Y to S into S, and this is exactly the pre-image. Pre-image of open subsets. And this preserves the frame structure. But there are arbitrary unions and finite intersections. So in particular, if I look at the points of X, which is a map from the one-point space to X, I can translate this into a morphism of frames that takes an open subset and produce let me use 0, 1 here. 0 if x is in, oh, no, sorry, 1. I set an open to 1 if my point was in the open, and 0 also. And now, if I think in terms of continuous functions, this is just the evaluation at the point x. So I'm preparing you to have this other point of view on topology where we transform everything into algebra. And so if you're familiar with commutative algebra, a point in an affine scheme is a ring morphism from the ring of function over X to the ground ring. That's the same idea. Why am I doing all this? To recall the notion of specialization between points. Set of point of a topological space as a natural pre-order. That's called the specialization order. So how does it work? Well, yeah, I should ask, I should add a remark here. In general, every point of X defines such a map, but there's not a bijection between points and maps. It's only true if the space is sober. And that's by definition of being sober. This is something that I want to put on the record. I'm going to assume that all spaces are sober. It's not going to change anything in what I say. So the set of points of X is a set of morphisms from the opens of X to 0, 1. Preserving its frame morphisms. And so now I have a canonical order here because this is supposed to be the topology of a point. So this is the empty and this is the 1 point sphere. So there's a canonical order here. And therefore I have a canonical order on maps. So if I have two points of X, I can say that X is lower than Y. For the order induced by the order on the values. And that's equivalent to an inclusion between the neighborhoods of Fx and the neighborhoods of Y. Every neighborhood of X is also a neighborhood of Y. That's what this equivalence relation says. Every open containing X, the function takes the value 1. And so if my thing is bigger, it needs to take the value 1 also. So if X is in U, this implies that Y is in U. And this is also equivalent to an inclusion between the closure and the inclusion is reversed. I don't know if you ever played with this specialization relation, but it doesn't really come up in topology unless the space are non-Hausdorff. So the relation red x is X is a specialization of Y. If we have this relation. So example in the fucking space, I can look at the point 0, and I can look at the closure of my point 0. Well, 0 was already closed, so the closure is 0. And I can look at the closure of the point 1, which is the whole space. And so we have an inclusion like this. And so we get that 0. Oh, wait, did I? I want to say that 0 is a specialization. Of 1 and the reverse relation is called the generalization. Did I get it right? I think I have a problem in my design here.
It's the other way around.
Yeah, it's the other way around. So that's why specialization of X. Anyway, it's not very important whether the relation is this one or the opposite. The thing that is important is that we have this relation and it's preserved by arbitrary continuous maps. That's the sense in which it is natural. So if 2 points are specialization of another, they have to be sent by a continuous map into 2 points that are specialization of another. One another.
But in terms, so you have your inequality, and then in terms of the inclusion, it's supposed to be the other way around. So if X is smaller than
no, I think this is correct.
in terms of the closure.
In terms of the, yeah, it's reversed. Those two, I think. What did I get? I got it wrong? No, I think.
Because 0 is included in the closure of 1.
I want the closure of 0, so I want 0 to be Y and X to be 1.
But then 0 is smaller than 1, or
yeah, but yeah, I want 0 to be smaller than 1. Okay, what did I? Did I get this backwards? It's possible.
I think that's the problem. The closure is the smallest closed set containing.
So that should be, so every open of X, every open neighborhood of X is also an open neighborhood of Y. So if I transpose this, I get that if Y is in a closed subset, then X must also be in a closed subset. Oh yeah, so that says this. Okay, yeah, thanks. Okay, so then it's back on tracks. And 0 is lower than 1 as it should. So using this relation, we can define a T1 space. The space such that this relation is the identity. And the T0 space is one for which this is an order relation, which means that it is antisymmetric. So otherwise, it's only a preorder. So now let's draw some pictures. So if I have 2 points and my space is Hausdorff, it means that I can find 2 neighborhoods that are disjoint. In a T1 space, I can find 2 neighborhoods that might not be disjoint. And in a T0 space, I can only find a neighborhood of one not containing the other, or the reverse. So these are various degrees of separations. How am I doing on time?
Oui, 11h30.
Okay. So let me give you some examples of T0 spaces and of usefulness for these order relations. So we've seen the Sierpinski space. It's an example of a T0 space, which is not T1. Another one is this one. Instead of 0 and 1, I look at 0 at n and with the order. And so the topology that I put here is that every upward closed segment is open. So this point is going to be closed. This is going to be open. And all the other points are neither closed nor open. And so that's a space. That's an example of an Alexandrov space. More generally, I could take any poset and look at the topology for which the open are exactly the upper stable subset. And so what is this space? Well, if I want to understand the space, I can either map from it or map into it. So if I map from this space into some arbitrary space X, what do I get? I get a chain of specialization between points of X. And if I map to this space, well, every element of n, I'm going to have a partition of X. It's not going to be an arbitrary partition, it's going to be a stratification. Where I define my stratification by a sequence of open subsets that eventually that start at empty and eventually is the whole space. So those examples exist. If I look at the space of n by n matrices, the canonical stratification, which is the rank given by the rank, the value in this space. And from this example, we can produce very canonical stratification. Say every time I have a map of vector bundles on a space, I can look at the rank of the map, and I can use this to pull back the stratification, and I get the dimension of the kernel, for example, of the map, or as a indexing a stratification. So another word for stratification that I could use here is semi-continuous function. Semi-continuous functions can always be understood as functions in those bizarre non-separated spaces. And they're actually continuous when we look at them here.
So n equal 2 is just, sorry, n equal 1 is just Sierpinski.
Yeah, for n equal 1, it's just Sierpinski. So it's a stratification of 2 open total space and 1 non-trivial open. Okay. Now that I introduced this idea that can be useful to have morphisms between points. Oh, I forgot to say that if my space is T1 or Hausdorff, every such map is constant. So it's more interesting to map into those spaces than from those spaces. Okay, so why am I telling all this? I have like half an hour. I'm telling all this because I want to introduce the idea that the space is studied by means of observables. And an observable is just going to be a continuous map, and it's useful to fix the codomain of the map. We call that the space of values of the observable. And so there's plenty of examples of this situation where we're going to study a space by looking at maps into a fixed space. So let's have a list. We have the discrete observable. I send X to the discrete space with 2 elements, 0 and 1, with the discrete topology. I can look at observable in the interval 0, 1, observable in R, observable in the Sierpinski space, and observable in a bizarre guy. There's 2 copies of the Sierpinski space that are glue at 0. So I have 3 points, 0 is closed, and 1 prime are both open. Yeah, I mean. So, and every time I can look at the kind of algebra that I have, every time the set of function from X into some given space is often going to have an algebraic structure. And in those examples, almost identified. So here, that's going to be the Boole algebra. For function with value in 0, 1, it's going to be a C-star algebra. Here it's going to be a C0 algebra, and here for the Sierpinski space, it's going to be a frame. And here doesn't have a name. And we're going to see in a minute why I'm introducing this guy. So now all of those examples, they have two distinguished points, 0, 1, 0, 1, 0, 1, 1, 1 prime, and 0, 1 here. So let me call that choice of such a space. Let me call that a gauge. And all the gauge of my examples, they have two distinct points. And so we can use that to have a formal definition of what it means to separate points. So let me use the letter A for an arbitrary gauge. And so I have two points in A. So I have a map from 0, 1 to A. And I'm going to say that the gauge is separating the space with a pair of points if there exists a continuous map from X to the gauge, sending my 2 points to the two distinguished points of the gauge. So let's see what it means in examples. So here I have to find a locally constant function taking different values on a point. So the best that I can separate with this gauge is connected components. I'm not going to be able to separate points in the same connected component. So if my space X is connected, every map like this is constant. So some gauges are kind of bad to access the topology. And that's kind of the idea here, is that we're changing the gauge to see more and more of the topology. If I use function in 0, 1, that's a very strong separation property, because it means that I can find between two arbitrary points an infinite number of closed subsets interpolating between 0 and 1 here. So it's a super strong Hausdorff condition. And I think it's called regular Hausdorff or completely Hausdorff. Something like this.
Normality.
Sorry?
Normality of some form.
It could be.
Regular is you can separate closed sets points, and normal is separate any closed set from any other closed set.
Okay, so maybe that's not what I want here. I think it's called completely Hausdorff, maybe.
Okay, yeah, sorry, normality was a red herring. I was thinking of Arizona's lemma, which is what you'd use
Yeah.
to construct these sorts of.
So yeah, so okay, so I'm going to make a remark about that. So this is a very strong separation property because there's not only there's something between my 2 points, but there's an infinite something. Now, if I use R, this is essentially the same thing. And this guy here, that's the Hausdorff separation condition. It means that I can find two open, which are the pre-image of 1 and 1 prime. And the other guy is just a closed guy, which is the pre-image of 0. And so this can be called a Hausdorff gauge. And I can introduce the Urisohn gauge, which would be a stronger gauge. So it's going to have 5 points, and I think -2, 0, and 2 are closed, and the other are open. Between 2 closed subsets, I can find another closed subset, not intersecting. So it's useful to formulate value separation condition in terms of those gauge and existence of a functions with value in some gauge, having fixed values at some points. So, where am I?
Sorry, if I can ask a question.
Yes.
So what about the case if you choose, so I guess this Urisohn this is one example of this. But what if you have a gauge where it seems that you could choose different points to be your specific points in the target?
Yeah.
How do you?
It's another gauge.
Yeah, it's just another gauge, but it's
Yeah.
changed the, I mean, it's not gonna, in some cases, it's not going to actually change. Like for instance, in the 0, 1 case, you're still gonna have this infinite set or whatever.
Yeah.
But in some cases, you'll have a different size, so then it's just considered a different one.
Yeah, you can, I mean, you can invent arbitrary separation condition where between the 2 points, you can have very various shape of closed and open subset inclusions or something.
Sure. Okay.
So yeah, that's what the gauge is doing. There's a lot of freedom. So why am I introducing those gauges? Because now we can see that we can see more or less of the topology of a space. So this does not see the connected components. Those gauges, they're not going to be able to see a specialization morphisms because they're both housed off. And so if X happened to be a T0 space, which is not housed off, all the other relation is going to be collapsed on the identity here. And so depending on the gauge, I can see more or less of the topology. And the Sierpinski gauge is the one where I see everything. And now what I want to introduce as an idea is that sometimes the Sierpinski gauge is not even enough. So we need to consider other gauges. We need to consider other functions with value in other spaces to be able to separate more some point. So when is it not enough? I'm going to take the torus and I'm going to let R act on the torus by some irrational slope. So let me call that R alpha, and alpha is not irrational. So people have various names for this object. So I don't know which one is the favorite here. People call sometimes the irrational torus or the non-commutative torus, or let me call that the irrational torus. So I'm looking at the quotient, so I'm looking at the space of orbits, and the topology happens to be trivial because every orbit is dense. Yes.
What's the action?
Oh, the action is okay. Let me do it on a fundamental domain. I look at translation, where the slope here is irrational. Right, so depending on the angle, my orbits are going to be closed or not. If the angle is rational, then I go a certain number of time and then I come back to the origin. But if the angle is non-rational, every orbit is dense. And so the quotient topology is trivial because the only saturated open subsets are empty or the total space. And so this is pretty bad because we have a lot of orbits, but we have no open subsets. And so that's a so-called bad quotient. And what is bad about it? Not the quotient itself, but what is bad is that we cannot use the Sierpinski gauge to access the topology of this guy. So we need to find other ways to access the topology of those spaces. Let me mention that this example is equivalent to the quotient of R by the lattice Z plus Z alpha, where alpha is non-rational. So here it's. And so how can we study those kind of spaces? We need to look at observables with valuing something else. And it cannot be any of those guys because they project down to Sierpinski, and we know that the observable in Sierpinski are trivial. So we need to find something else. So I'm not going to give an answer immediately for this space, but I'm going to make a couple of suggestions of other gauges that we can consider and that are considered in topology. So instead of looking at functions on my space X, I can look at the collection of all vector bundles on a space X. And so I want to think of a vector bundle as some kind of continuous function with value in the space of vector spaces. I can another example that maybe will help to understand the first one, that I can look at covering spaces of a given space X. And I can try to look at this as a function that sends a point to the fiber of the covering space, which is a set. I can look at sheaves over my space, which are local homeomorphisms over X. And again, this looks like some kind of functions, continuous function from my space to set. And every time the idea is to look at the fiber of what is there. So I send X to the fiber of my map at X. There's other thing that I can do. I can look at functions of my space with value in a spectrum in the sense of algebraic topology. And so that's just the cohomology of X with value in E. And so there's a lot of other space of functions that we study for a given space, which have value in whatever. And that's a problem. That can we make sense that a vector bundle is actually something with value in some space of vector spaces, or that a covering space has value in some space of sets, or that a sheaf is another kind of function with value in a set of space. So maybe for two different topologies on on sets. And the answer is yes. there exist several examples. So how much time do I have left? 10 minutes. Okay. So so let me forget about the cohomology example. And let me remark that those spaces, if they exist, they cannot be topological spaces. Because it's easy to see that there is no topological spaces with this property of classifying all vector bundles or covering or etc. We can if we cheat a bit. So for vector bundles, for example, if we use homotopy classes of maps, then we have some kind of classification like this with value in some infinite Grassmannians or something like this. But that doesn't work for those guys. So how can we access those spaces? Well, that's the beginning of my talk. That was the introduction. And so there's essentially two ways to build those kind of spaces. So this is, I'm not going to have the time to enter the details of that, but I'll be happy to discuss it further in next week or whenever. So I'm going to make a couple of remarks on how to think of those spaces and not yet to formally define them. That would be for either another talk or a talk around a coffee or beer. So something interesting about those spaces that they should have a category of points. Because vector spaces, naturally, they don't form a set. I can look at the set of isomorphism classes of a vector space, but this is a kind of badly behaved invariant. And because I cannot glue isomorphism classes of vector bundles. I can glue vector bundles, but not isomorphism classes. And so it's useful to remember the symmetries of those objects. And so the three invariants, they're better behaved if we look at them as categories. So there's a category of covering space, and there's a category of sheaves. And let's see. So the space of vector bundles has a category of points, and the space of sets has also a category of points. And now, it shouldn't be so surprising. We've seen that a topological space, a good old topological space, can have a preorder of points. So going from preorders to categories is a small step. I mean, it's a big step from the point of view of topological spaces, because that's going to give us headaches if we try to understand what is the corresponding spatial object, which is to preorder, which is to categories, what preorders are to topological spaces. And so there are several answers here. So the theory of topos is one answer. The theory of stacks is another answer. So let me try to find a punchline. So we need to think Let's see. So to justify this idea, let me think a bit about what is a vector bundle on the Sierpinski space. It has 2 points, 0 and 1. And so there's several definitions actually of what could be a vector bundle over the Sierpinski space. But certainly it needs to have 2 fibers, 0 and 1. And now I have my specialization morphism between 0 and 1. And so I can use it to define a vector bundle over the Sierpinski space as a map between vector spaces. Vector spaces. And so this says that my bundle, if I look at it as a map, it sends point to point. And morphisms to morphisms. That means that the morphisms in those bizarre spaces, they have to be think as being some kind of specialization morphisms. And they're going to say how points can be transformed into each other. Yeah. Sorry, I'm running out of time here, so let me think. What could be a punchline? So they're not. So there's 2 strategies to access those spaces. Topos and stacks, very different strategies. So let me say only a word about the topos strategy. The idea of a topos strategy is to do exactly what we've been doing before, is to use a gauge. And so we need a gauge, which is, if I want to capture some spaces with a lot of morphism between them, which are very not separated, I need a gauge which is as badly separated as those guys. So a topos is going to be exactly the good old topology, but we're going to change the Sierpinski gauge by the space of sets. And so I cannot define the space, because how can I define it? It's like defining the Sierpinski space outside of topological spaces. Well, I can't. But the idea is to say that I know if this is a topological space, I know what a continuous function with value in the space should be. And that's enough to bootstrap the theory. And I'm going to say that this is a sheaf or a local homeomorphism over X. So I think of this as a continuous family of set. And so a local homeomorphism can be a thing that way. So over each point, I have a fiber, and the fiber has a discrete topology because of the assumption on the map. And so the fiber is a set. And so as I move around in X, I change my fiber. The cardinal of my fiber can jump up and down. And I want to think of this as a continuous map with value in the space of sets. And so if I look at the collection of all continuous map from a given space to this, that's the category of sheaves of sets on X. And that's going to be the equivalent of the poset of open subset to study the topology of the space by means of this gauge. So I think I'm going to stop here for some questions.
So what about the stacks? What is the strategy?
So yes, strategy for the stacks is not to use observables. Not so the topos. So the topos, what we do is that we axiomatize the algebraic structure of this guy, and then we define a topos to be a category having this structure. It would be like axiomatizing the property of a frame and say that the space is just a frame. For the stacks, the idea is kind of the same, is that I can completely understand the space if I know all maps, all continuous maps from good old topological spaces. The new spaces, they behave well in the sense that we can know them entirely by mapping out of proper space. And so here we're going to define every stack is going to be a functor. Defined on topological spaces. And to each space, I'm going to associate the continuous maps from X to my guy. So that's going to be the interpretation of what is there. So for example, category of vector bundles over X defines such a functor, because every time that I have a map, I have an inverse image, and that defines a functor. Strictly speaking, it's a pseudo functor, but let me forget about that. And so we're going to consider those functors, and we have a unit embedding. Let's say that any topological space is going to provide one of such functors. And so this is a way to get a bigger, we can embed topological spaces into some much bigger category. And the stacks are going to live inside this setting. So there's a good reason to consider that. I can only say a quick word about this. It's a way to complete this category by forming some quotients that behave nicely. So all the quotients that were bad in topological spaces, through this embedding, they're going to be, this embedding is not going to preserve them, and it's going to send them to better quotients, which do not live in topological spaces, but which behave nicely. So another name for this functor is, this could be called a moduli problem. Any moduli problem always defines something. I want to classify a structure. I look at a functor that sends X to the family of those structures, indexed by X. And I always get such a functor. And after that, this functor is nice or not. So we need to, that's only the very beginning of the theory of stacks. Anyway, I'd be happy to discuss it further with whomever is interested.
Can I ask another question?
Sure.
So what is example of the irrational topos? So then what?
Yes, good. Yeah, good question. So it can be faithfully. Yeah, good. I almost forgot to say that. So with irrational torus, it's completely captured by a topos. So I can look at sheaves over the space, and this is the same thing as equivariant sheaves on T2. So it's a good old sheaf on the torus, together with an action of R, which lift the action on the base. And that produces a topos. And that's a very good invariant. And from this topos, we can compute invariants such the RAM cohomology. And we can prove that in the H1, the RAM, which is going to be R.
That's some sort of smooth structure.
Yeah. Yes, correct. Yeah, to compute the RAM, we need to introduce a smooth structure, but it will because the torus has a smooth structure and the action is smooth. And so everything is going to behave nicely. And so I can compute the RAM cohomology, and the one forms are going to be R. And inside, I can reconstruct the lattice of period. And so I can reproduce alpha. I can produce alpha from the topos as an invariant of this space.
This is going to be different to equivariant homology.
So up to an SL2Z action, which is a symmetry of this lattice, we can reproduce alpha. So using the topos, we capture this guy with a lot of structure. We get much more than the set of orbits. We get some kind of topological feature, which is not encoded by opens, but which is encoded by sheaves. And there's enough sheaves over this guy such that we can even reconstruct the slope of the action.
Philosophically, are you taking a topological space and then imposing additional structure on it, or are you creating something totally new?
It's something new. The idea is we have the category of topological spaces, and we can embed it into the category of topoi, or into the category of topological stacks. And actually there's even an embedding like this. And those embeddings, they don't preserve quotients. And so if you look at
The diagram is commutative.
yeah, the diagram is commutative. And so if you have a group acting on a space here, and it's a let's say it's a Lie group, or let's say a discrete group, to simplify. I have a discrete group acting on X. The action doesn't need to be nice. And because if the action was nice, then the quotient would exist here. So I take a non-proper action. And I look at X and G as topoi now, and G is still acting on X. But the quotient of the action is different now. So here we have a naive quotient, which is bad, because for the topology is trivial, for example. And here we have another quotient, which is no longer a topological space, but now behave nicely. So that's where this guy is computed. This quotient is recomputed in this category. And it's not preserved. It's not the image of something here.
Sort of forgetful function or something like that.
Yeah, you can. You can truncate a topos to get a good old topological space.
And then the X bar J, you cannot recover the naive quotient.
No.
Maybe you don't want, but
No. So if you send this guy back to the world of topological spaces, you get the naive quotient. And so you get you lose the topology essentially.
But you are somehow putting additional structure on topological space.
If you want, but it's I'm not sure I would say that like this. It's like somehow if you think that the topology is a structure on a set of points, then you can think of a topos as another kind of structure on the same set of points. But that's a bit rough to say it like this, but.
Okay, very good. Are there any other questions or remarks in the audience, including the people on the web? Okay, so let's thank the speaker.